Okay. So first, standard forms. First order standard form is given by that, and yeah, is given by that. Whenever you model a system and you have a transform function which you can manipulate or rearrange to appear in this form, then just know that the gamma, the constant which multiply this fraction is actually a gain of that system, and one upon one by tau s, the tau is actually time constant of that system. So as an example, we can consider RC network. This is RC network. You are familiar with this. I know you did this in ECT. So, but I'll just show you a quick way of how to get transfer function of this, and then we can also use it, apply it to other problems. So the way I do this, let's say I want to find V2 over V1, I just know this is a voltage divider, and then I transform the capacitor in terms of domain as this. So whenever you see a capacitor, just know in S domain is 1 over SC, provided that the initial conditions are 0. And then what I do is that V2, V1 is actually this value here, divided by the total impedance, which is R plus that. So you have R plus 1 over. So what you can do, you multiply both sides by SC here to make it 1. You multiply by SC, it becomes 1. You multiply by SC, you have 1 plus SRC. So that is the quickest way to get transfer function. So if you have an inductor, you can just have SL. Is that okay? Rather than doing a lot of arithmetic and differential. So this is the fastest way of you just transform capacitor as 1 over SC and inductor S over L, and then you treat them as impedances. So with that, we can have our transfer function for this system as 1 over 1 plus SRC. So comparing this equation here with the standard form, we can say our gain is actually 1 gain of the system, and our time constant is RC when you compare these two. So another second order standard form is given by that. We have two forms of this. You can either have it this way. Another form, I'll show it in other lectures, maybe next week. So whenever you see you have a second order system, you can actually present in this form. This is gamma, gain again, and then you have 1 plus 2 zeta over omega n. Zeta is actually damping coefficient. It's this is unitless coefficient, and this is natural frequency. And okay, this is wrong. It needs to be squared here instead of 2. So, and that is squared omega squared n. For RLC network, as I said earlier, so you can just say that is R SL 1 over S, and then say you have V2 over V1 is equals to this one here, C plus divided by, sorry, R plus this and plus, sorry for the handwriting. So you can just multiply a C to make it nicely. After that, you'll have something like this. So from here, if we compare this equation as you see RC, the SRC with here, with this standard form, we can actually get zeta damping coefficient. Also, this one will enable us to get the natural frequency. So once you have natural frequency and you plug it here, you can actually get the zeta damping coefficient. So these are the standard form. There is another standard form which we discuss later, that in terms of Poisson zero, but also these ones we can use. So once we have modeled a system and we have it in a given standard form, then the whole point is to analyze that system. Remember that we say we are actually transforming this equation, linear differential equation, into S domain so that we can easily manipulate, and then later on we go back and invert it into time domain to see the response. So that is the whole idea of Laplace transform and these forms. So once we have our system and we want to check its response in terms of time response, so we say the manner in which dynamic system responds to an input that is expressed as a function of time, we call that as time response. And time response has two components. Remember, in your differential equation engineering maths, you are able to find two components of an equation in terms of solution. You had transient response and steady state. So the transient response, this is part of response that goes to zero as time increases. So just when we look at this is our input to a system. So we have a system, we have injected an input, that is a step input, and then after we have injected an input, the system produces this curve, this oscillating curve. So this is the output. So the output is oscillating. This part, before it goes to zero or stabilizes, that part from here to here, that is a transient response. That is a transient response. And this transient response, actually, sometimes it will have a sustained oscillation, meaning oscillation will go on forever, and that is very bad for a system. So we want a system which, once it has responded, then those oscillation of transient response goes to zero, or they decay. So the other part which remains after the transient response has died is actually a steady state response. So this part on is actually a steady state response. And when the steady state response is the same, when the steady state response is the same as the input response, then we say we don't have a steady state error. But if there is a difference between here and the input, then we say we have actually a steady state error. So the way we do this with actually we inject as an input to a system, and since so many systems we don't know which type of the input it is. So what we do actually in time domain analysis, we use test signals or input signals. And these test signals are normally step input, ramp input, parabolic, and impulse. So these, you can see this is the step input. So when A is equals to 1, then we say we have a unit step input. When A is equals to 1, we say we have a unit step input. Same thing with a ramp. When A is equals to 1, we say we have a unit ramp input, a parabolic, and an impulse. An impulse, this is actually denoted with a delta. You know this from your, I think, communication. So that is an impulse. So area of this is that is equals to 1 at t is equals to 0, and at t not equals to 0, the whole part is actually 0. So what we do is actually we inject these signals into the system, and we see how the system will respond. So for like step input, it's like you are switching on. So the way you simulate, you put step input, step input, unit step input, and see how the system will respond when you switch it on. So this is when you are increasing velocity, and this is acceleration. So the actual input signal of the system is usually unknown, as I say. Hence, standard test inputs are used, and these are the 3 or 4 standard state input signals. Remember, our system, the way we model it is in terms of transfer function. So, and it is in S domain. So the way we do is that these step input, the step input ramp, we actually need to get the RS. So this is RT. RT is in time domain. We need to get RS of it. So that is in S domain. So Laplace transform of these LT Laplace transform pair of step input is actually 1 over S. So if it is a unit step input, you have 1 over S, because A is equals to 1. If A is equals to 1, if you have something like that, and this is for the parabolic. For the impulse, Laplace transform of it is just equals to 1. So this is your system. You have model, you have transfer function. You want to know how the system will respond, the output. So what you do, you inject this. So you inject this, and then you see your output. So once you have that, you get your CS, and then that CS you revert it back to time domain by using inverse Laplace transform, as we'll see next. So applying input. So you have RS, as I said, as your input, CS as your output. So the way we did with block diagram algebra, we know that CS is actually just GS times RS. So this is, let's say this is GS. So GS. So for unit step, you just multiply 1 over S by your transfer function GS. For unit ramp, 1 over S squared. That for impulse is just 1. So for impulse, CS is equals to GS. CS is equals to 1 over S squared GS, and CS is equals to 1 over SGS. So the way we do our time response analysis is first, the way we determine time response of a system. First, we apply input to transfer function, as we saw here, and then we simplify if it's necessary. After that, what we get from from applying the input signal to it, we use inverse Laplace transform tables to convert from S domain back to time domain. So as an example, actually this is a unit this is a first order closed loop feedback system. So you have 1 over Ts as forward gain, and then feedback loop is actually 1, because we say whenever you are told this is a unity feedback, then it means HS is actually 1. So we know our closed loop overall transfer function is given by that, and G is that, and H is 1. So substituting those, we end up with this equation. So CS over RS is given by that. That is our transfer function for the whole system. So CS output is actually RS into that. So let's say our input step is our input signal is actually unit step. Then it means from our table here, this is actually 1 over S. So we have 1 over S onto your transfer function. You simplify, you end up with this equation. But from the tables of Laplace transform, you can't find something like this so that you convert it back to time domain. So what we do is we use a partial fraction method to split this, and then later we take inverse Laplace transform. So once we do that, we'll end up with our time domain response as 1 minus exponent minus d over tau. So this is the partial fraction method. What we can see, so we have this. So we want to split this so that we can easily read, we can easily change CS into time domain. So what we can do, I want to remove this. How do I remove? Okay, you can just ignore these lines next for the next picture. So what you have CS. Again, this is engineering maths. I think the third year. Yeah, when you are doing Laplace. So what you do, you say A1 over S, this S, A2 over S plus 1 over tau. So these are the denominator, you split it. So you get LCM, that is this times that, and then A2 times S. You rearrange, collecting like terms together. So you have A1 plus A2 upon S plus 1 or A1 over tau is equals to 1 over. So this part is similar to that. So we equate these same terms, and then we get A1 is equals to 1. And A1 plus A2S, we don't have any term of S here, so it means A1 plus A2 is actually equals to 0. So A1 is equals to minus A2, but we know A1 is equals to 1, so A2 is equals to minus 1. When you put these, you substitute A1 here as 1 and A2 as minus 1, you end up with this equation. So taking inverse Laplace transform, so we know that 1 over S is actually just 1, and 1 over S plus tau, 1 over tau is actually, so whenever you have something like S plus, let's say A, then no, it's Laplace in time domain is given by that. So our A here is this. So we just have 1 minus tau t. So this is our time domain, our time response for a first order system. So whenever you have a first order system, you'll get a response similar to this. So these are common partial fraction expansion. This is what we use, but sometimes you can have something like this, and you can also have something with a quadratic and an S at the origin or something. So you can actually use this. I'll post this picture so that you can refer, or you can just refer from your notes in third year. I think in third year. So first order, so we have this our first order time response, 1 minus e t over tau. So when we just want to plot or a sketch, so when t is equals to 0, this goes to 1, so 1 minus 1 is 0. When t is equals to tau time constant, so we have 0.6332. So this is actually 63.2% of the final value. So when time is actually a time constant, then it means that the output has reached 63.2% of the final value. When tau is actually 3 tau, 3 times tau, you have 0.95, almost very close to the final value. When it is 10 tau, we are actually there. So at around 4 tau, we have a steady state error of 0.02. But actually, for first order time response, steady state error is actually 0. And when time constant is small, it means that your response will be faster. As you can see here, T1 is less than T2, so T1 actually has reached to 0.632 faster than T2, because T2, you see T2 is here, so it takes time when time constant is larger. So time constant actually indicates how fast the system reaches final value. Another thing we need to know is the steady state error. So we know error is actually the RT. This is the input minus the output. So input minus output. This is actually, sorry. So we know our input is 1. Our output is 1 minus that. So 1, when you open this, you'll end up with this exponent. So we want to know steady state error is the value when t is actually in infinity, or t is very, very large. So when t is very, very large, it means this value is actually 0. So steady state error for a time first order system is actually equals to 0. We can also find steady state error using in S domain. So we have ES is actually RS minus CS. Doing some manipulation, you end up with error in S domain as given by that. So for our first order system, we know GS is that. So you multiply you use your GS here, and your step input is 1 over S. So you end up with ES given by that. So we can either use this or that to get a steady state error. So this one we showed, you just plug in infinity here, and then you find ET is equals to 0. but we can use final value theory. We know steady state error is actually when t goes to infinity of et, but remember lim t is equal to infinity et is the same as lim s is equals to 0 s e of s. Remember we did this I think last week. So we're using final value theorem and applying into here. You multiply by s and you apply your 0. You set s to 0. You end up with ess also equals to 0. So the way we are doing this equation is the same as here. Now you can see it's very simple, but later you'll see that most of the time you need to use this method for you to get ESS or steady state error. So here we can say that the output of the first order system approaches reference input, that is our input RT, without any error. So in other words, you can say a first order system tracks the input without any steady state error. So example is the open loop plant transfer function of a unity feedback linear time invariant control system is given as this. Actually, I gave this question, part of this question was in last exam. I think I gave them 4 marks for this. Yeah, similar question. So use Laplace transform to derive an expression for the time response and sketch response for the unit step input. So you have this, and you are told that this is a unit feedback. So you need to get CS. So you know that CS over RS is GS plus that. Your unity feedback is 1, so you plug it 1 there, and you know GS is given by that 1 over S. You rearrange this, you'll end up with 1 over S plus 3. Apply here, he said what? And sketch response for the unit step input. So your input is actually a unit step. You know your RS is 1 upon S. You apply that using partial fraction. You end up with CS 1 over 3S minus 1 over 3S plus 3. Applying Laplace inverse Laplace transform. So applying inverse Laplace transform, this one it will be just 1 over 3, and this one, this is constant, is 1 over 3, and that one is E minus 3 over T. So you have your nice equation there. Just some sketches, T of an output 0, 0, 0, 0, 0 like that, and then you do a small sketch, and you have your marks, 4 marks. So that was an example which actually was a question in last year paper. So another thing we need to discuss is different inputs, same system, first order system, but now a unit ramp. So for a unit ramp, we have RS1 over S squared using same output, apply using partial fraction method and inverse Laplace transform. So for this you use yes, for unit ramp someone need to turn off to mute his mic. I don't know who is this. Let me check. I'm getting some feedback. Let me just continue. So everyone is okay with this example? You okay with this example? Class,
Yes,
someone
yes.
to respond, please. Okay. So next thing we need to do is applying a unit ramp. So this actually needs to read. Sorry. This needs to read unit ramp, not step. Unit ramp. So we need to apply unit ramp, which is 1 over s squared. So applying that using partial fraction method. So I was saying you can for this one you use this. So k 1 over s squared s plus s squared into s plus a. So you use this for the repeated root. So you apply partial fraction and taking inverse Laplace transform, you'll end up with st as that. So when you plot output and input, will end up. So this is our input, which is a nice straight line from the origin. But for the output, we'll have some delay here, and then it goes up, being parallel with RT. So from here to here, this is actually a transit response, and then going here is steady state. And when we try to get error, which is RT minus CT, we'll end up with that equation. Applying t to infinity, this will go to 0. So we have tau times 1, which is just tau. So steady state error for unit ramp in a first order system is actually at constant. So for you to have a very small steady state error when you're using unit ramp, so it means you need to have your time constant small, because steady state error is equals to time constant. So the steady state error is equal to time constant of the system, as shown here. For smaller time constant, steady error will be small, and the speed of the response will increase. So in terms of lectures, I just wanted to present or to capture till this analysis, that is unit ramp for the first order. So if you have any question, you can ask. Later slides are actually just solutions for the assignment and the exercises I gave you guys past weeks. Is there any question? Okay. So last week I gave an exercise that is just a practice exercise for the block diagram reduction. Most guys who they did, I think there were only 17 who did this, and most of them got it. So I'll just go through it quickly. This pickup point was here. So when we shift ahead of it, then it means this GR will actually divide H2. So once we do that, GR will be here. Multiplying GR and G2, we have G2 and GR in cascade. So another thing we can do, we can move this also here ahead of this block. So once we do that, exactly same thing as we did in previous we have H1 over G2, G3. So this goes here. So we have G3, G3 and G2, G3. And here we have H1 over G2, G3. We can see that this part is actually a feedback, a closed loop feedback equation. So that closed loop feedback equation, we can absorb this by applying G over 1 plus GH, where our G is this G2, G3, and our H is H3. So once you do that, you'll end up with this, and that one multiplied by G1. We have G1 and that equation, and these two are actually being added here. This confusion for most of you guys was on these two. So these two, you can just add them, and then you have another feedback loop which you can absorb. So this, the whole of this is like a big G, and that is H. So using closed loop absorbing using closed loop feedback, you end up with that equation. So some guys actually did till here, which is okay, but you can first simplify. You can multiply 1 over G2, G3 on up and down. So if you multiply that, that will cancel, and if you multiply that, this will cancel. 1 plus G2, G3 will be here. So this one will be here. From here we have that, and then also these G2, G3, they can cancel there. You open this, you end up with G1, H1, G1, G2, H2. So that is the required solution. Why we want to have something like this? Because later on we'll be using the denominator, which is actually a characteristic equation, to do some analysis. So it's good that you have in this form. I know some guys are saying, "Sir, are we tested to simplify or to get a transfer function?" Okay, it is transfer function, but it's good to have it in a standard form, the way we know it, because there is a reason why we do that, because the denominator later, when we equate it to 0, then that denominator, we use it to do some analysis, and we call that a characteristic equation. So assignment 3, question 1 solution, I've posted today. You can look at it for the state variable. Remember the field control DC motor, you need to get differential equation, state model, block diagram, and transfer function. So make sure you go through it and understand. I won't discuss it today, maybe next time.
Excuse me, sir. Regarding the
Yes.
in the second part in the assignment, I was wondering whether the state variable, are you allowed to choose different from the ones which you choose? Like your state
actually yes.
Oh,
you're
yeah.
saying?
It's okay, you're answering. Yes.
No. Okay. The good thing is, the thing is, you need to get all the independent variables. Like in our case, we chose IF, right? I think we chose IF, and then we chose what? We chose theta, which is displacement.
Yeah.
Right?
Yes.
and then we chose angular velocity. You can choose two, because you can choose, but I think all those three are actually independent, because later you'll also need omega in your output. So I think it's okay. It's okay, because in theta we also actually describing omega, because that is a displacement and another one is a velocity. But it is good practice that you absorb all the variables or independent variables. Solution will be okay, yeah. But I'll prefer you guys you absorb all the variables.
Oh, okay. And then regarding the
So
CAT, we had scheduled it for November 13th, but that week is the same week that the supplementaries will be taking place.
yes, I've also noticed that. So we can push it. We can push it to which date? We can push it to the other week.
Yes.
After supplementary.
Yes.
So you discuss with your.
I think it's going to be 20th.
20th.
Yes. Or 27th.
Yeah. So you need 27th or 20th.
Okay.
Which one, 27th or 20th?
27th. The supplementaries end on 20th. So 27th is when we're going to be, then when they're going to be over.
So you guys are okay for 27th as our cut one?
Yes.
Yes.
Okay. So next class is actually what we okay, today what we did, we show standard forms and then test inputs, different types of test inputs or input signals, and then we went on and discussed time definition of time response. We also got time response for first order system, analyzing using unit input step and unit input RAM. And then we also got time response for both and steady state error for both. So next time we'll do same thing for second order system, and if we have time we'll do error analysis. And for tomorrow, I won't be able to have a class tomorrow, so you guys, I'll post question tomorrow morning for you guys to practice. So these are just practice questions. I'll post them under exercises, so you can go on and do some practice. So I won't. I hope that is okay. That tomorrow we want to meet. I'll be busy with my research. If it's okay with you guys, then we can do time problems, and then we meet next week.
It's okay.
So I need a word from you guys. If it's okay, then we meet next week.
Yes, it's right.
Yes, it's okay.
Hiyo mmesema haraka sana. So let's meet next week. I'll post questions, and make sure you go through the solutions which I posted today. Also notes, I'll post notes for today's class, and for the next week classes, I'll post them next week. I'm a little bit busy between today and Sunday. I hope you can bear with me with that. Thank you.